zeros. It's been like fun. Oh, yeah. Yeah. Axes are does it change it on? It's right in the corner, right, where it has X and Y, just scratch out where it says X and Y there. Yeah, but it doesn't change which is shouldn't change. Well, do you have any do you have any version or like the structure? There was a structure with vertical beams, yeah. And it's very like horizontal and yeah. For the beam that's transverse for the beam between transverse for the spaces, it should be all next. Yeah. Well, you're talking about the bit with the springs? Yeah. Oh, yeah. Okay. Yeah, like I know that, but you gotta really that's yeah, adding these. I only have the two classes. Well, three if you include the design project. Oh yeah. But there's somebody turned up and so I guess it's a lot of it. So far it's only been research. Like research what other people have done, write a report on it. Yeah. That's what I signed up for. I didn't sign up for the research project. I signed up for the design project. Yeah, but they have to like apply for the funding, so no. All right, I don't think there's gonna require much funding, just really print a few parts and get a few screws and bolts to hold together. Getting you all like the actual or the electronics stuff. We have that. So oh, yeah, it's already robot built. I just need to redesign one of the legs. Oh, okay. And that's all going to be 3D printed. Or maybe it's a stage like action. After I've got the leg design, we get to assemble it. This will be a few weeks of testing. How big is it? Oh, okay, that's small. Yeah. That's like, so how many legs will there?
There are 6 driving legs and 1 steering leg.
Okay, and where's the students like front? And then-
It's in the back.
Oh, the tail.
Yeah, so it walks on 6 legs, and then there's 1 leg in the back that turns it.
Mm, I'm guessing the steering wheel gets rounded, right? Okay. Like, how's it gonna like, it kind of needs to grip from the ground.
So far it's been tested on asphalt, sand, and grass, and it's
Oh, okay, well, those are
not
like,
really
rough.
too perfect.
Well, what about like, like marbles?
I mean, I don't think there's much demand for a robot that walks exclusively from
Well,
marble.
maybe like a rich person wants like a different type of room, but maybe.
If it's a smooth level surface like that, you can just use wheels.
Well,
You don't need legs if it's.
what if it's like the.
All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Hanging in there. All right, so last time I saw you guys, we had the midterm on Tuesday. I haven't looked at them yet. I'm planning to grade them likely on Monday. That's just I'm kind of backlogging on some things, but I do want to get them back to you before next class. So you can expect, if you want to pick up your exam, you want to see it. Next Tuesday is going to be the day when I give it back. But I haven't started looking at them, so I have no idea how things were or not. Okay. But to kind of take a break from all that, today we have our next ANSYS activity. So today is ANSYS activity 2, the bike crank activity, right? So if you go to Canvas, so I was a little bit late in posting this. I posted this, really like maybe an hour before class started, or before my other class. And so if you go to the Canvas site, you'll see that there is a new assignment for ANSYS activity 2. So you go ahead and click that. So there are 2 files to download this time. So there is the PDF, that is the instructions. So that's what we're going to be going over today. And the other file that you need is the CAD file. So that's the file that we're going to be running our analysis on. Okay. So make sure you download both of them. You can start up ANSYS as well. So it takes a couple minutes to start up ANSYS. And so if you kind of remember from the first activity, the way you start up ANSYS is that you go to your start menu, you go to where ANSYS is installed, and you want to open up the program called Workbench. Okay. So if you're in the lab today, the program you want to open is Workbench 2021 R1. If you're working at home, if you're working on the student version, it's probably going to be Workbench 2024, 2023 R1 or R2. Okay, just whichever is the latest version of ANSYS, you want to open up the Workbench program. Okay. All right, so once you guys go ahead and do that, go ahead and open up ANSYS, and then we'll spend today doing the project. All right, so I think that is it. Are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. So go ahead and open up ANSYS Workbench. Okay. And we're going to be doing a simulation on a bike. Okay. So the idea, if you don't know what a bike crank is basically this the part that connects the bike and the pedal, right? And so it's the part that cranks the bike forward. Okay, so you push down on it with your foot to kind of propel the bike forward, right? So the kind of the setting for this activity, or kind of the motivation, is that you're going to be working basically for a bike crank manufacturer. And we're going to see, basically, we're going to run simulations to see if the bike crank is going to fail under the given loading or not. Okay, so compared to the first activity, obviously this activity, we're using a much more realistic geometry. A geometry that's already made for you, so we're not going to spend any time making our own geometry here. We're going to be assigning our own material properties and applying the loads. Okay? So compared to the first activity, there's not nearly as much instruction here, so it's not going to be as kind of hand holding as the first one. Just because you have all the knowledge from the first activity as well as all the knowledge that we've gained from everything we've learned so far in the direct stiffness method. And so this activity is going to be more for you to kind of take what you've learned from ANSYS, take what you've learned from the direct stiffness, and kind of apply it to kind of a more realistic problem. Okay. So let's go ahead and start up Workbench. Okay. And so first thing we're going to do here is we're going to create our analysis system. So if you remember, the way we did that was that we looked on the left-hand side here under the toolbox, and we need to choose what type of analysis system that we're going to run for this activity here, okay, or for the simulation. So the one that we want, the one that we're going to be running our simulation on is static structural. So go ahead and click and drag static structural into the project schematic. Okay. And so once you do that, it's gonna open up a window here, okay, where we're going to be operating on our activity. All right. So is everyone open up Workbench, and everyone has this part open right here? Good. Okay, so first thing we're going to do here is we're actually going to be adding a custom material property. So we didn't do this last time. So last time we basically just used one of the materials that was already kind of built in by default into ANSYS. So this is a really useful skill. So a lot of times when you're running finite element simulation, you're going to be using either materials that your company is using, or you're using a material that's not kind of built into ANSYS already. So knowing how to specify a material, specify a new material based on its properties is something that's really valuable. Okay, so to specify a new material, we're going to go to engineering data here. And we're going to double click on it. And so as soon as you double click on engineering data, the window here is going to change quite a bit. Okay. And so it's going to show you basically all the different materials that are available to you. And so if you look at kind of the center of the window here, right? The center of the window here basically tells you all the materials that you currently can use. And there's only one, and so you should only see structural steel in there, right? So what we're going to do is we're going to add a new material. And so to add a new material, you're going to click on the box here that says click here to add a new material. Okay. And so as soon as you click on that, it's going to let you type something in. And so let's go ahead and give our material a name. Okay. And so of course this is a completely custom material, so you can name it whatever you want. So you can name it pee pee poo poo if you want to. But usually it's useful to name your material after the material that's actually being used. So the one that we're going to be using in this activity is an alloy of aluminum, and so it's aluminum 6061 T6. Okay, so go ahead and type in the name of your material and hit enter. And when you hit enter, it's going to create a new material here in your engineering data. Okay. All right. So if you notice here, after you create your data, after you create your material, there's kind of a blue question mark kind of next to the material here, right? So whenever you see a blue question mark in ANSYS, that's basically ANSYS's way of telling you that we need to specify more information and more data before moving forward, right? Because all we've done so far is we've just given a name for the new material. We haven't specified any of its properties at all. Okay. Okay. But from here, you actually have a lot of different options. So there's lots of different types of materials that you can specify, or lots of different types of properties that you can specify for your material. Okay. So if you look at kind of the left-hand bar here, right, you'll see that there's lots of different kind of properties. So you can specify the physical properties, linear elastic properties, hyperelastic properties, plasticity, creep, height, strength, all different kinds of things. And all those different properties are used for different applications. But for a lot of applications, you only really need to specify kind of a small portion of this, okay? For our case here, we're going to assume that our aluminum is an isotropic linear elastic material, right? So that means we're going to specify isotropic elasticity. So while you have the aluminum 6061 T6 highlighted, you can either click on the row or click on the box itself. What you're going to do is you're going to go to the left-hand side of the screen and you're going to double click on isotropic elasticity. Okay. And so as soon as you do that, that's going to open up the properties window kind of in the bottom center here. Okay. And then you can actually start typing in the material properties. Okay. All right. And so if you look at the bottom middle of the screen here, you'll notice that there are two boxes here that are in yellow. Okay. So that's ANSYS's way of telling you that you should specify those two properties in order to kind of fill this out. Okay. So there's two properties we need to fill in there. We need to fill in the Young's modulus and we need to fill in the Poisson's ratio as well. Okay. So for the Young's modulus, you can see that the default here is to specify the Young's modulus in Pascal. But if you look at the problem document, you'll see that the Young's modulus for our aluminum is actually given in PSI. Okay. So let's make sure we switch the units here. So for the Young's modulus, make sure you switch this to PSI. Okay. And we're going to input the Young's modulus of 1 times 10 to the 7th. So in other words, 1E7. Okay. All right, so you're going to enter 1E7 and then hit enter. Okay. And you want to make sure that you're in PSI. That's kind of the #1 mistake people forget in this assignment. So not change the units for the Young's modulus. Okay. Okay, so the other thing we're going to input here is the Poisson's ratio. And so if you go back to the problem document, you can see that the Poisson's ratio for this bike crank is 0.33. Okay. So we're going to enter 0.33 here. Okay. Okay. So all we've done for this is we've defined a new material, aluminum 6061 T6. We've defined it as a linear isotropic material, and we input the two material properties that are needed for it, which is the Young's modulus and the Poisson's ratio. Okay. Any questions on this? Yeah.
How do you know the material is isotropic?
Yeah, it's a good question. So usually for most metals are going to be pretty isotropic. Just because the molecular structure of the metal is pretty uniform in all directions. And so that basically means that the strength is going to be the same in all directions like that. So most metals behave like that. There are exceptions, of course. It really kind of depends on the type of material that you have otherwise. And so if you have something like a wood material, so wood materials kind of have usually they have a grain direction. And so you're going to have more strength in that direction. And so for those ones, I would specify an orthotropic elasticity type of material for that. So it really depends on the type of material that you're using. A composite material is going to behave differently, like a carbon fiber or something like that. So it's every material is a little bit different, but for the most part, most metals are pretty isotropic. Yeah. Any other questions on this part here? Okay. All right, so let's go ahead and close out of this. And so we've done everything that we need to in the engineering data. So let's close out from this tab. So if you go to kind of the top ticker here, there is a tab called A2 engineering data. And so you can just click on the X to kind of just exit out of that. Okay. All right, so that'll bring us back to Workbench here. So the next step here is we need to import our geometry. Okay. So unlike the first activity, where the first activity we kind of drew our geometry from scratch, here we're going to import it because we've already, someone else has already made the CAD file for us. Right? So this is pretty typical. So a lot of times when you're running finite element analysis in a company, you're either going to create the CAD file in another software. A lot of times that's going to be software like SolidWorks or CATIA, or someone else is going to make it for you and give you the file. Right? So to import a geometry, you're going to right-click on geometry here, and then you're going to go to Import. And then you're going to click on Browse on this button here, right? And so what this will do is that this will open up a file explorer where you can upload or import the material, the CAD file, right? And so if you haven't done so already, the CAD file for this activity is given. And so if you go to the Canvas site under ANSYS Activity 2, you'll see that there's an additional download here for crank underscore assembly dot x underscore t. Okay. So let's go ahead and import that. So to import the geometry, you can either double click it, you can click it or click it and open, either one's fine. Okay. And you'll notice that after you do so, there'll be a green check mark next to the geometry. So that basically tells you that the import worked. Okay. Okay. All right. So the main question I usually get in this part here is you know, what are the file formats that are accepted by ANSYS, right? So if you notice the file format for our you know, the part that we just imported, the file extension is x underscore t. So you know, Windows is kind of they're kind of misidentifying this, and so Windows may think that this is a SolidWorks file format, but x underscore t is actually a file format called Parasolid. Okay. So Parasolid files work. Another file format that's very common is an IGS format, so that's .igs or .iges. Okay, they both work. So I would say those are kind of the two most common ones that are used. A file format that won't work is a direct SolidWorks default file format. So that's SLDRPRT or something like that, right? So the pure SolidWorks file is not going to work with ANSYS. And so if you want to take a SolidWorks part and import it in ANSYS, you need to convert it to one of these file formats here. So either IGS or the one that we're using right now, which is x underscore t. Okay. So that's kind of an important part for this. And the main reason for this is that SolidWorks and ANSYS are separate companies, and so they don't want to share information about their file formats. And so, you know, you have to convert it. But luckily, you know, SolidWorks does have a way to easily convert the files. And so when you have your part or your assembly open in SolidWorks, all you have to do is just save as. Okay. And then you save as just one of these other file formats. But you do need to convert a SolidWorks file to one of these in order to use it with ANSYS. Okay. All right, so now that we've imported our geometry, we are ready to open up ANSYS Mechanical. So go ahead and double click on model here. So when you double click on model, it's going to open up ANSYS Mechanical. Might take a couple minutes to do so, but it'll get there eventually. Okay, so after you imported your geometry and after you've checked to make sure it's okay, you can open Mechanical, and you should see this this screen here. Okay. So from this screen, you can see that we can see our bike crank here. Okay. So on the one side, we have these kind of three holes, and so these are the holes that attach the bike itself. Okay. And on this side, we have the pedal side. So this is the side where normally a person is going to be pedaling down this. Okay. The pedal itself isn't there, but the little kind of shaft that comes out is there. Okay. Okay. So is everyone able to open ANSYS Mechanical and you see the part kind of as it is here? Okay, good. All right. So the first thing that you should notice about this part is that there are actually this is actually an assembly, and there's three different parts of this assembly, right? So part one is the crank itself. Okay. Part two is this little shaft here that comes out for the pedal. And then part three is this little kind of mating ring that kind of fits in between the crank and the pedal itself. Okay. All right. So the first thing we're going to do here is, you know, because our analysis is mostly focused on the crank itself, we're going to learn how to suppress different parts. Okay. So this is very common. So when you're working with finite element analysis of kind of pre-made CAD files, oftentimes, you know, you don't need every part in the assembly. You want to just focus your analysis on the part that you want to focus on, right? All the other parts are just mostly just going to create dead space for you. So they're gonna chalk up you're gonna gunk up your mesh, or cause your simulation to be more expensive than it is, okay? So to get rid of a part or to suppress it from your analysis, what you need to do is you need to go to the left-hand side of the screen, you're gonna go to the geometry tab. Okay, you're gonna expand that menu, and then from here, you're gonna see all three of the parts. So you can see that we have bike crank 2 Rev 2011 X 0.375. We have the pedal 0.375, and the part 9 caret SM2 Rev 0.375, right? Okay. So all we care about is the crank. So we don't really care about the pedal or the mating fitting at this point. So to suppress a part, all you have to do is right click on the part that you want to suppress. Okay. And then you're going to click on the button for suppress body. Okay. So go ahead and do that. You can do that for the pedal, or you can do it for the part 9. Okay. And if you notice that as soon as you do that, then that part disappears from the image here. I'm gonna do the same thing for the pedal. So let me right click on pedal here and then click on suppress body. So then that gets rid of the pedal as well. Okay. All right. So make sure you do that. Make sure you you clear the other two parts. Okay. All right. Okay. So the next thing that we're going to do here is we're going to assign a material. Okay. So remember, we defined that kind of custom aluminum material. And we want to make sure that we actually assign this to our geometry here, okay? So under the same geometry menu, so under the same menu up here, okay, you're going to click on the bike crank object itself, okay? So bike crank 2 Rev 2011. And then what you're going to do is you're going to go to the bottom left-hand side of the screen, and you're going to see that there's an option here for material assignment, okay? All right, so right now the material for this crank is structural steel. And so we want to change that. So let's go ahead and click on structural steel here. You're going to click on this arrow to kind of expand the menu outwards. And then you're going to change the material to your aluminum material that you defined earlier. So go ahead and click on aluminum. And then that changes the material assignment. Okay, so that changes the material of this pipe. Okay. Any questions on that? Everyone able to suppress the parts and assign the materials to the bike crank? All right. So that's all the new stuff for this part. And so the next step here is going to be the meshing. And so if you go to the problem document here, let me go ahead and scroll down. Okay. We've done everything up until meshing here. So your next goal here is to apply meshing settings. Okay. And so you're going to the main thing that you're going to set here is the size of the elements. Okay. And so if you follow the document here, it's going to say to create a method and sizing object. That's a little bit overkill. And so the only thing that I need you to do here is specify the size of the elements here. Okay. So when you left click on mesh, it's going to ask you for the element size here. Okay. So go ahead and assign a size for the mesh. So if you just generate the mesh by itself, it generates a mesh that looks like this. This looks like a pretty poor looking mesh to me, just because it's very it looks very pixelated. So I would much rather see a much smaller mesh compared to this. Okay. And if you want, you can change the units as well. So I think the default units is millimeters, but you can change it to US customary inches as well. Okay. So from the 5 inches. Smaller. Okay. So you could try different settings for the mesh. There's a lot of different meshes that'll work for this one. Again, this is still a relatively simple simulation, so there's a lot that can work. But your mesh should look, roughly something like this. So you should have a pretty good mesh density. In particular, if you kind of rotate the part on its side, right? you can see here that we're kind of looking at the thin dimension, right? If you look at this kind of cross section here, you should see kind of multiple layers of elements going across. Okay. This is really important and kind of a really good metric or good to know for finite element meshes in general. And so whenever you have a mesh of a relatively thin object like this, you should be able to see kind of multiple elements through the thickness. And so it shouldn't just be one element across like this. The reason for this is that generally speaking, when you're making a finite element mesh, you want to have a good amount of what's called interior nodes. So nodes that are kind of on the inside here that aren't on the outside edges, right? And so to do that, you need to have kind of multiple elements through the thickness of the part. Okay. Okay. So you want to avoid cases like like this. Let me generate the mesh. Okay. You want to avoid cases like this where you have kind of one element that kind of goes all the way across the structure like this. So you want to have a good amount of elements through that thickness. Okay. Ideally you should have maybe like 3 or 4, but even just 2 elements makes a world of difference. Okay. All right, any questions on the meshing here? Okay, so this next part, I'm going to let you guys work on yourself a bit, but now you need to specify the boundary conditions. Okay, so that means the loads and constraints. Okay, so just like we do for our direct stiffness problems, we need to have at least one fixed support. Okay, so to remember to apply boundary conditions, you're going to right click on static structural A5. You're going to go to insert, and then you're going to apply a fixed support. Okay. I also want you to apply a force, and so you're going to right click on static structural A5, go to insert, and you're going to click on force here, okay? And so that lets you apply a force in a certain direction. But I want you guys to kind of determine where these boundary conditions are applied, and even more particular for the force, I want you guys to determine, what direction makes the most sense for the force. Okay. Okay. So for the force, remember the way that I generally like to do it is I like to specify my force in components. And so when you click on the force right here, if you go to the bottom left of the screen, okay, you'll see that there is a setting called define by. And so instead of defining it by the vector, you can define it by the components. And so doing so will let you specify the X, Y, Z components of the force kind of individually, right? So I think that's a bit easier to kind of specify. So, I want you guys to determine kind of the direction and location of the force, but I want to give you guys a couple of hints. Okay? So remember when we first kind of opened up this file here, I mentioned that the side of the bike crank with the 3 holes, this is the part where it attaches to the bike itself. Okay. Whereas the other side of the bike crank with the single hole, this is where the pedal usually is. So the pedal side is where a person's going to be applying their force, applying their weight, okay? And the bike side is where it's going to be attaching to the bike frame. I want you guys to simulate I want you guys to use finite elements to simulate kind of a worst case scenario. Okay? So think about what the worst case scenario would be in terms of, causing this bike crank to fail or to rupture, okay? So the worst case scenario would be like, let's say you're biking along and you get something caught in your bike chain, okay? And so it causes your entire bike, crank here to kind of seize up, okay? And so what would be the direction of the force that you would apply that would be most likely to cause this bike crank to rupture, okay? So I am going to limit you. So I'm going to limit you to 100 pounds of force, okay? So the total magnitude of the force that you apply should be no greater than 100 pounds, okay? And so the main decision that you're going to make is what direction of this force, right? what direction of this 100-pound force to apply. First of all, where to apply it on the bike crank itself that would cause the highest amount of stress. Okay. All right, so I'll give you guys maybe just 5-10 minutes to work on that, and then we'll kind of move on to the next part. Okay. But if you're having issues, if you're having problems with this activity, just raise your hand and I'll come by and help. Yeah.
Are you limiting us to 100 pounds total?
Total, yes. The magnitude, so that you're applying the force as a vector, so the magnitude of that vector should be 100.
Wait, how much? It's not really. Yeah, this part is really this fits to this, so it rotates.
So the geometry there, that's the location you're going to apply. And so that's a particular portion of the geometry. So I would change.
It could be, yeah, so it seems like.
Edge.
I
would have a very good surface.
So maybe it's like three holes fixed onto this. Yeah, well, that's a good example. So. This one is just. Probably the small one. Sure. So, well, we're not the course. Oh, you're right, yeah. It could be a little stuff, but then this thing is shut, so it could be a. So things hold this and the bearings. Yeah, the actual like thing. Yeah, that could feel. Small areas, like, that's a lot of stress. So I can see that feeling basically in here. Okay, so. Where? It's in this direction, it's going to be even. It's going to be feeling.
Question.
More of this way. It's like a shield. Yeah, you made this way experience more than that. Essentially, the direction is one of those actually is like
I think we'll experience more stress than you. That's true. That's true.
They're not gonna. Yeah, that's, I don't, well, kicking up, that's kind of hard. Or like pulling back. I kind of think they will make this.
This one.
Right.
This.
Or we can also like change the actual. Yeah.
It's a different direction, but it can still.
Yep.
All right, how's everyone doing? Everyone still applying their boundary conditions? Okay. All right, so I'll let you guys play around with that a bit more. You know, I'm gonna show you how you can check your results right now, okay? All right, so now that we have the mesh, now that we have the boundary conditions, we are ready to run the simulation. But before we run it, we need to specify our output field. So we're gonna right click on solution A6. We're gonna insert. So first thing we want to see here is the total deformation. So make sure you specify that as one of your output fields. The other thing we're going to specify here is the equivalent stress. So we're going to right click on solution A6, go to stress. Make sure you click stress, not strain. And you want to view the equivalent stress. Okay. Okay. All right, so let's go ahead and click solve. Okay, solve with the lightning bolt that's kind of at the top of the screen here. Okay. All right, and so if you apply your boundary conditions, you know, you should get a stress field that may look something like this. Actually, let me turn off the grid here just so it's a little bit easier to see. Display. Sculpt here. Edges, no wireframes. Okay. Okay. So you can see here, I have a stress field that looks like this. And so my maximum stress is about 13,726 PSI. Okay. All right. And so depending on the direction and depending on the location of your force, your stress may be different, right? And so if you did not get this stress that I'm getting here, or at least in this distribution, you know, you may want to kind of reevaluate. Okay. Maybe change the direction of your force, maybe change the location. Okay. But to give you a hint in terms of how I obtained this, right? Basically, whenever you have a situation when you have a beam or anything that's fixed on one side, the amount of, or the loading situation that's going to cause the most stress or the most danger of breaking is bending, okay? And so you want to think about, you know, what direction that you want to put your 100-pound force to force this bike crank into a bending mode, okay? And so if you're not getting a stress that's as high as this, you know, you may want to change the direction of your force, okay? Okay, so that's the first thing to do. So first thing I want you to do is I want you to find the direction of force that would put this cantilever beam in bending, okay? So that you can kind of recreate the same, you know, the same stress that I'm getting here, okay? And the stress is a really important field to analyze in ANSYS. And in fact, it's one of the more powerful things that you can do in ANSYS. Because basically you can test whether or not your part is going to fail by looking at the stress field. Okay, because every material has a property known as its yield strength. Right. So the yield strength of the material is the maximum amount of stress that it can sustain before it breaks or before it goes through plastic deformation. Okay. So for the material that we're using, has a yield strength of 35,000 psi. Okay. Okay. So that means that, you know, we can keep loading this, or we can keep increasing the force on this bike crank, you know, continuously until we reach 35,000 psi, and then that's the point where the bike crank is going to fail, right? And so for the last part of this activity here, I want you to find out what's the maximum force, or what's the maximum load that the bike crank can handle before it fails, right? So basically, I want you to take your force here, and I want you to increase its magnitude until you reach a failure point, okay? But I want you to do this with a safety factor of 2.0, right? And so what that means basically is that I'm going to take my yield strength, I'm going to divide it by my safety factor of 2, okay? And so that gives me a maximum force of about 17,500 psi. And so for problem 5 of the activity, I want you to, you know, once you do, well, it's kind of shown on the screen here. It's kind of a spoiler, but you know, once you have your force in the y direction like this, you know, I want you to steadily increase the force until you reach a maximum stress of 17,500 psi. Okay. So the way to do this is that you're going to go to your force boundary condition. You're going to increase this, and so let me increase it by 5 pounds. And so instead of 100 pounds here, I'm going to change it to 105. Okay. I'm going to rerun my simulation. And I'm going to see what the maximum stress is. So the maximum stress is given by the maximum value of this colored line right here. Okay. Okay, so you can see that when I increased the load to 105 pounds, the maximum stress increased to 14,412 psi. Okay. And so you would basically keep increasing the force until you reach that maximum, force of 17,500. Okay. Okay. All right, so that's the activity there. Okay. So not too much for the not too much with the ANSYS stuff. It's just a lot of things that you kind of play around with. The second parts of the activity also have some additional problems for you to do, just like the first ANSYS activity, right? So problem 6 on the ANSYS activity is to utilize your frame code, right? So remember last week we worked on this code in MATLAB that we developed to simulate frames under the direct stiffness method. And so first thing I want you to do is I want you to simulate this the structure right here using your frame code. Okay. So you're going to input all 6 elements here. You're going to input all the material properties. You're going to run the code, and what you should get is the solution to be this. Okay. So problem 6 here is just applying the frame code that we worked on last week to this problem. Okay. Then problem 7. Problem 7 is the assignment that I told you about at the end of class last week, where I want you guys to implement a 2D truss code from scratch. Okay. So basically take what we learned, take kind of the whole methodology, take the logic that we developed for the frame. And I want you to do that for the truss here, okay? And so here I've kind of written you kind of a step-by-step process, or step-by-step instructions to do that, to kind of help you out, okay? All right, so that's the plan for the rest of class today. So for the rest of class today, feel free to kind of play around with this simulation as much as you want. Change the mesh, change the loading. I want you to find out what the maximum load that the structure can withstand in terms of pounds, okay? And then from there, you can work on the map stuff, right? Any questions on any of this? Okay, all right, so I'll let you guys work on that. And in fact, actually, I'm not sure if I posted the completed frame code, so actually, let me do that. Just so you have it for your reference here. So we go to week 8. Add this in here. All right, so if you either don't have your code right now, or if it's at home, you can download the completed frame code here, right? So if you go to week 8, the page for week 8 on the Canvas site, you can download this MATLAB code frame underscore FEM underscore code, and that has the completed frame code that you can use for problem 6 on this activity. Okay, but of course the trust code you have to write yourself, so you have to write that from scratch. All right, and so if you have questions, if you want me to look at your code, if you have questions on the activity, just raise your hand, and then I'll come around and help you guys out. Yep. Yeah. Exactly. Yeah. Using the direction. The perpendicular direction. It's the direction. For this one, it's symmetric, so it doesn't matter. So you can do minus y or plus y. It doesn't. Yeah, I mean, the difference that you'll see here, that is your minus y down here, then, because the whole thing's gonna be thin. So you do minus y, then this part here will be in compression, and this top here will be in tension. But if you do positive y, it's the opposite. So right now it's compression.
So that's why we did not decide to mention.
Exactly, yeah, but because it's symmetric, you kind of said it just reverse. With the equivalent stress is convenient because it shows you just one number for the stress itself, but it doesn't tell you which direction the stress is. Now, you have no, I mean, if you're just looking at this just by itself, you have no idea how the force will apply. You have no idea if that's your tension or force in the light. That's kind of the downside. But it's convenient because it's just one number.
So everything one that listens is what do you mean? Yeah, right. They usually find it.
Oh, you can.
What does that mean?
Like what is the full? It would have like more elements, right, like small pieces. So let's see, let's just see some.
Open certain. So, this,
Yeah. Well,
so here.
oh, well, that's true. Okay. So make sure it's selecting the edges. So. See that. No keys. Oh. And then. So you see the keys. Well. This is because otherwise it will probably click the other time. Thanks.
We can write this.
I think it lets us fit. Let's see one more. Let's see. Yeah. Let's see. Oh, it's still. Yeah, change. Okay.
Maybe it's on the, I don't think it's the wrong thing, but maybe.
It's all the interface.
So here, that.
So,
Very really true.
I think it's because like our elements are always so soon. Yes. So we put the edges first, and it's like
It did go together. Yeah.
it's like you know how it's like when it's like a sharp edge. It's like this yes, like concentrated. Let's see. I could do it on mine. Let's see. Oh, so. It's fine. You got a lot.
Oh, you can just take a, like a snippet. So if you want to, if you want to save the screen, there's two.
And so. You wanna? Yeah, yeah.
Thank you. Yes.
Thank you.
Yep, have a good weekend. All right, guys, it's 6:45. You guys are welcome to keep working here. I think we're the last ones in here for today. Actually, let me stop this so I don't get in trouble.